Today I'd like to share a heat exchanger design template that I've been working on for some time. This is a tool that can be used by both engineering students in chemical and mechanical engineering, but it can also be used as a first estimate for your engineering consulting firms, right? So if you are a heat exchanger company, consulting firm that does design or does verifications and things like that, it's a nice tool to start with. So this tool will be available online in the next coming weeks, and for students obviously there'll be a discounted price, to help you validate your work. So it is not meant to be a shortcut for your design. However, it is there to validate. So I have an example today that I'd like to work through from your design textbook. So it goes: design a condenser of the following duty: 45,000 kgs an hour of mixed light hydrocarbon vapors to be condensed. The condenser is to operate at 10 bar. The vapor will enter the condenser at 60 degrees C, and the condensation will be complete at 45 degrees C. The average molecular weight of the vapor is 52. The enthalpy of the vapor is 59 596.5 kilojoules, and the condensate is 247 kilojoules per kg. Cooling water is available at 30 degrees, and the temperature rise is to be limited to 10 degrees C. So that is your temperature rise of the cooling water, which is a very, very important design basis. So when you're developing a design basis, this is something that you would add as well. Plant standards require tubes of 20 millimeter OD, 16.8 millimeter ID, and 44.88 meters long, of admalty brass. That's a difficult word, but it's brass, right? So that's something we need to consider. And then the vapors are to be condensed, and subcooling is and no subcooling is required, right? So we'll have to check that statement. I don't completely believe it, but we'll see. Okay, so what I decided to work with initially was methane, ethane, propane. But one thing I quickly realized when I was doing this example is that methane will create a need for subcooling. So what I ended up doing was I ended up removing the methane, right? And to make it easier, I also removed the butane, and then I only worked with let's make that 0. I only worked with propane 50% and ethane at 50%, right? So where do you start with such a problem? So technically you have a design basis, right? What the question itself can be summarized as a design basis. And what needs to happen is your job is to find a unique answer basically for the question. So let's get to the template first, right? So one thing to note is that my this design template, right, was built in conjunction with, right. What you'll need to do is you'll need to adopt the design template to be able to accommodate to the simulator. We're first gonna do manual calculations to check the size of the cooling water stream. It's important to know how to do the manual calculations. Yes, there are tools like DWSim, Coco, Aspen. However, right, especially for the students, it is important for you to be able to start from the beginning so that you understand the concept. Okay, so we've been given the info. We know that the inlet temperature is 60 degrees. So we're going to go 60 degrees plus 273.15, right? We know that the outlet temperature, let's go back and check. The outlet temperature is supposed to be 45 degrees. So we're going to go 45 plus 273.15. Just confirm that we're using the right values. Now, where will we get the CP, right? This is where now it's either, right, you can go to your manual databases where you will get the CP, or I'm not the student, so I'm gonna do a shortcut. Or what we're going to do is we're going to create a stream with the same conditions on Coco on DWSim, right? So we're gonna have a material stream. Let's see if this works out. So okay, so let's have two material streams, one for the water. What's going on here? Okay, give me a second. Okay, so we're gonna have two material streams, one for the water, one for the methane. So let's start with the methane. So the methane, we know it's the flow 1,000 kgs. So for 5,000 kgs, which can then translate to, we divided by 3,600, and that will give us 12.5 kgs an hour. So if we go back to this, we can go 12.5 kgs an hour. 12.5. Know that our pressure is supposed to be 10 bar. We know that the inlet temperature is supposed to be 333.15. Right? We're not doing much here. We just want the properties of the stream. So we're gonna go 0 there. Ethane is 0.5. Propane is 0.5. And butane 0, water 0, and we're gonna accept that stream. Those of you who haven't used DWSim before, I really like DWSim as compared to Coco as an open source software. It gives it's easier to add new compounds on DWSim. Also, the software itself is quite nice to use and the visuals are quite good. And one thing I've realized is even the one thing that's a bit of a, I would say, a drawback, the material stream itself is not as organized as I would like. So most of the time when I use DWSim, I end up having to first organize the material stream myself. But overall, the software is quite nice. It's quite nice. And then let's do the water. So water, let's just assume, as they said, it's coming in at 30 degrees. So let's go and add that as well. Inlet temperature plus 30 plus 273.15. Outlet temperature, we said it's going to be increasing by 10 degrees. So it's going to be 40 plus 273.15, right? So what I want now from DWSim is mainly your heat capacities, right? In terms of the enthalpy of the vapor and the condensate that were given in the question, and that is 596.5 and 247. So 596.5 and 247. You'll see. So because you are condensing, you're gonna have a heat of condensation, right? When you are evaporating, you're gonna have a heat of evaporation. So to calculate that, you get the enthalpy of the vapor, enthalpy of the condensate, and you subtract the two, right? So we're doing heat exchanger schooling as we go. So let's go back to our streams. So now I don't know the flow of the water, right? But what I'll do now, right, is to fully define the stream at the temperature that we're starting at. So it's 303.15, right? I'll fully define for now. Need to make everything changes. Refresh that, and already you'll see it will have defined, right, the stream for me, right? So the two streams for me. So now stream 1 let's go back and confirm which is stream 1. Going to the flow sheet. Stream 1 is your it's your light hydrocarbon stream, where stream 2 is your water. So stream 1, if we go to it, I'm going to check the CP. So heat capacity of the vapor is 1.978. So we're going to put that in. Heat capacity 1.978. So as I said, this is technically a cheat code, right? Because you would need to go to the databases and search for the CP of propane and the CP of butane, or we're doing propane and ethane. So you'd need to search for the two, and then you would need what the CP will be. Simplify things, we use the a simulator itself is using a correlation, right? So it's using a property package. In this case, I've chosen correlation, right? So it's an average. Okay, so next we go to the liquid, which is joules per kg, and immediately you'll see 118.78 kgs per second, right? So next we can now do a simulation of the exchanger, because now we have the properties of both streams, and at the same time we can now get the properties that we need to fit into the property stream. There's a very special, or it's my template, so everything feels special. But the good thing about this template is all you need to do, it does not matter what is stream 1, what is stream 2, what is stream 3, right? The spreadsheet itself will auto detect which is the property, which is the tube side, and which is the shell side. Because in this particular template, right, we've chosen that the hot stream will always be in the tube side, but this is something that can be your engineer and where they can select whether they want the fluid in the shell side or in the tube side. All right, so let's get to our simulation. Let's go back to our values. So we know that our cooling water is at 118.78 kgs per second. So we're going to input that. So stream conditions, 118.75 kgs per second. 0.75 kgs per second. Now let's go back to our it. DWCM before would like a tutoring session that will show you how to navigate the system, please do contact me. Sessions are priced for students at 450 rands per hour, and then in terms of graduates and people who are in the workplace, this is something that we would have to decide on. Contact me, I would love to assist you. As I said, DWCM is a beautiful package, but I know that most universities still prefer to use Cocoa as a free software. But start introducing DWCM. This is a message to all the lecturers. This is a very nice software. It doesn't take away from the learning, and it is very close to simulators like your Aspen. The only difference is, just like Cocoa, the limitation is the property databases. But as I said before, right, it is much easier to add compounds on DWCM compared to Cocoa. I am not advertising between the two. It is just how I find it easy. So I'm looking forward to hearing from you. Let's continue. All right, so we're going to use a exchanger, not just a cooler, so that we can represent both streams. So I'm gonna put in my exchanger. Okay, so I like arranging things to look nice. Okay, so stream one, stream two. All right, and since we've fully defined both inlet streams, all we need is to define what we want to do on the heat exchanger. So when you click on the exchanger, it will give you these options. Now these options are what you want to do with the exchanger. So I'm gonna go with counter current. I love counter current. Counter current advantage. Oh, go read up about it, especially the students. But it allows you to it allows you to circumvent the idea of approach temperature, where your cooling stream, right? You can have a crossover in terms of temperatures, whereas in cold current you cannot have that. Okay, so what are we trying to do? As we said, we're trying to condense the stream, so we can specify the outlet molar temperature. So you need to check which stream you're looking at. So just want to confirm here. um, Outlet vapor of stream 1. So stream 1 is our product, so that's the one we want to condense, so that's fine, and we put that at 0. So if you click solve, you will see the problem is fully defined and it will run. The one thing you need to understand about simulations, and the reason why I did the manual calculation, right? The simulation is not there. The simulator is not there to do the job for you. You are supposed to define it. You are supposed to give it the basis of your calculation, and it must be able to find a unique solution. So that's what we did here, right? And if we go to our material stream, we will see that our material stream has now been completed, and we're going to copy that to clipboard and paste it in our raw data. So I just want to show you how the spreadsheet looks now. You'll see there are no calculations, nothing has been done. Input data, there is nothing on the input data. There's nothing on the input data, as you can see. So what we're going to do now is we're going to paste our raw data just overlay it on them, and immediately we can come and see that it has auto populated. Now, as you can see, right, the tube side, as I had indicated, right, is the product, which will be moving from 333. Give me a second, something looks off. 333, something looks off. I need to check if it is taking the right streams. Something does not look right. Hot feed temperature 333, cold feed temperature 303.15. So why is it not reading correctly? Let me go back and check. So it did properly identify the hot feed and the cold feed. However, so hot feed has been properly identified, that's fine. Cold feed has been properly identified. What hasn't been identified properly is the outlet, which I need to go back and understand what happened there. So I'd like to pause this session here for now, so that I can go back and check what I missed. The spreadsheet was working quite nicely before, so something went funny. Need to check that. So we'll pause this session here, and we'll have session 2 once I've corrected the error. Okay, again, if you need help with the WCM, if you need help with getting started with your design, especially for students, sessions are available at 450 rands an hour.